What would happen if you could compress the entire sun until it fit inside a city just 6 kilometers wide? The answer to that question takes us to one of the most extreme phenomena in the universe, and to understanding why we need different physical theories for different scales of reality. A star is a giant ball of gas under constant tension. Gravity pulls all the material toward the center. The pressure from the hot gas pushes outward. As long as these two forces remain balanced, the star stays stable. During the 19th century, physicists like Homer Lane and Robert Emden managed to apply classical mechanics to the interior of stars. They developed mathematical models describing how pressure, temperature, and density vary from the core to the surface. It was an extraordinary achievement. The same laws that describe planetary motion could explain the internal structure of stars. But what happens when a star exhausts its nuclear fuel? For stars of moderate mass, the answer is a white dwarf, an object the size of Earth with the mass of the Sun. Here, quantum mechanics provides stability. Electrons, by their very nature, resist being compressed beyond a certain point. In 1935, Subrahmanyan Chandrasekhar calculated that this resistance has a limit. If the stellar remnant exceeds approximately 1.4 solar masses, electron pressure is no longer enough to support it. The collapse continues. This raised a question that classical mechanics could not answer. What happens to matter that keeps collapsing with no known mechanism to stop it? To understand what happens under these extreme conditions, we need a different theoretical framework. Classical mechanics describes gravity as a force acting between masses in a fixed space. This description works extraordinarily well for a vast range of phenomena: planetary orbits, tides, the structure of normal stars. Einstein's general relativity offers a different description. Spacetime is not a passive stage, but curves in response to the presence of matter and energy. Objects are not attracted by a force. Instead, they follow the most direct paths through a spacetime that is no longer flat. In most situations, both frameworks give nearly identical predictions. But under conditions of extreme density, general relativity predicts phenomena that lie beyond the reach of the classical description. In 1939, Oppenheimer and Snyder mathematically demonstrated what general relativity predicted. When a sufficiently massive star collapses, no known physical mechanism can stop it. Space-time curves so dramatically that what we call an event horizon forms, a boundary beyond which all possible paths, including those of light, lead toward the center. It's not that something traps the light. The geometry of space-time itself offers no route of escape. This is a black hole, not an object in the traditional sense, but a region of space-time with properties radically different from anything we experience. For decades, black holes were a theoretical prediction. Many physicists, including Einstein himself, doubted that nature would actually allow such extremes. In 2015, the LIGO detectors recorded gravitational waves produced by the merger of two black holes. It was the first direct detection of these waves that Einstein had predicted a century earlier. And in 2019, the Event Horizon Telescope achieved something that once seemed impossible: photographing a black hole. The image shows the supermassive black hole at the center of galaxy M87, surrounded by a ring of glowing gas. What began as mathematics became direct observation. But general relativity also has its limits. At the center of a black hole, where the equations predict infinite density, the theory breaks down. It's a sign that there is physics beyond what we currently understand. This is perhaps the deepest lesson. Every physical theory has a domain where it works and boundaries where we need something new. Classical mechanics brilliantly describes the everyday world and ordinary stars. General relativity extends our reach toward gravitational extremes. And somewhere, there is an even more complete framework waiting to be discovered. Scientific progress is not about replacing incorrect theories with correct ones. It's about constantly expanding the limits of what we can understand.